Today we are going to talk about PyTorch. So this lecture is not intended to be a beginner's tutorial. We are covering many different topics in PyTorch because I'm assuming many of you have already know some basics of PyTorch. So this lecture is intended to cover many different aspects and tools that is in the PyTorch ecosystems that you might miss if we didn't cover and discuss it. And also, this week we will have a homework discussion, a new homework this week, which we will discuss later in this lecture. Okay, so this is the outline. We'll begin with some basic introduction to the PyTorch. As we mentioned before, this is not a full beginner's tutorial, but we'll cover some basics and some important points that you might miss. And then we will cover many different tools in PyTorch ecosystems. I think one of the reasons that PyTorch is being successful, which you know that in the framework of deep learning frameworks, that there are two major competitors. That one of them is PyTorch and the other is TensorFlow. Of course, there are other frameworks that also do a deep learning, like JAX for one, and there are also some others like MXNet, things like that. But two major ones are PyTorch and TensorFlow. In recent years, I think PyTorch is winning this war of deep learning frameworks. So why PyTorch is winning? There are many different reasons. One of the reasons is that there are some properties and some essential fundamental difference between the ecosystem of PyTorch and the TensorFlow. In a simple way to explain that is, I think the reason that PyTorch wins is similar to the reason that the Python is winning, because it is more focused on the people that are not familiar with programming and coding, so that people can a very large population can have access to these tools. So we'll talk to this a little bit later. But first, we are going to talk about PyTorch and PyTorch ecosystems. And finally, we are going to talk about the homework 3. Just like the first two homeworks, we are going to draw some images. But this time, we are going to use machine learning. You can use the tools that we introduced in previous weeks. That is like SVM, linear regression things, or other logistic regression, or other tools in scikit-learn, like random forest. Or you can also use the PyTorch to build up neural networks to do the same thing. Previously, the homework is specifically for the tools for in scikit-learn. But I think people are more used to or more familiar with PyTorch because deep learning is getting much more popular. So if you are more familiar with PyTorch, it is okay to use PyTorch as well. So that's why I include this homework after we introduce the PyTorch. However, like we probably emphasized before, that this is not a PyTorch beginner's tutorials. So if you were not familiar with PyTorch, then this lecture alone might not be helpful for you to actually have the ability to write a neural network classifier, either a classifier or a doing the regressions. So you won't have that ability just right after this lecture. Maybe with a little bit extra practice, it might not enough, but you can still use the tools that we introduced in the scikit-learn. And we have a lot of different notebooks that covers the topics of machine learning, like classifier or regressor. You can use those notebooks. And we also provide notebooks as an example for homework, but you still need to write your notebooks by yourself and submit to the homework. So let's begin with the introduction to the PyTorch. Okay, let's see. This is homepage, the official homepage of the PyTorch, official website of the PyTorch that I just get a screenshot from it. And you can see that just like other tools that we introduced before, like NumPy, scikit-learn, or Matplotlib or Pandas, it has something like a learn or document. So these two sections provide you enough materials so that you can learn the PyTorch by yourself, and you don't need any more like a textbook or other like blog post. You can actually follow the official document to learn the tools very well. I think this is a very important skill, that you develop the ability to learn tools by yourself in your own way, because there will be new tools developed and created in every years. So it is impossible to cover every tools. It is easier if you get the ability to learn these tools. And fortunately, if a tool is getting popular, open source, especially an open source tool, is getting popular, most of them have a similar characteristic or similar way that you can learn it. One of them is the official website, because one thing that makes them popular is that they have a good document. So as you can see, that NumPy, Pandas, or Matplotlib, or even like scikit-learn, and in this case PyTorch, they all have similar architecture of their official website. They almost have a get started, quick start or beginner's tutorial, and they also have a full documentary. So this is how you can learn it. I think like 3 years before, I won't recommend you to follow the PyTorch website. I still recommend you, if you want to try some to learn some practical basic for deep learning, I would suggest you to learn it from the TensorFlow document, because TensorFlow also have a very comprehensive document, and it is practically the beginner's guide to practical deep learning. However, as I check it, the PyTorch document is improved a lot and getting very comprehensive. So it is right now, it is very good start point if you want to learn the practical deep learning. If you are already a very, very beginner, another tools you might want to try is Keras, because Keras also support TensorFlow and PyTorch together. And Keras is still a very good tools for beginner if you want to construct a network quickly. But I'm not going to introduce Keras in this lecture. I'm just mentioning it because I don't think people use Keras that much in if they are trying to use PyTorch. However, if we only evaluate the tools itself, I would say that Keras is still one of the easier frameworks for beginners, and still a lot of people like programmer that without the background of like AI background or machine learning background, when they want to try something like deep learning or machine learning, from what I heard, they still like Keras a lot. Okay, before that, you can see that I use the red pen to circle out the ecosystem because one of the reasons, like I mentioned before, that is PyTorch have some personalities that allow it to build a large ecosystem, kind of like Python, because they are very easy, accessible, and easier to understand for beginner, not for expert or not for, I mean, when I say expert, I mean for the programming expert, not for a machine learning expert. So a lot of machine learning expert or mathematics expert or computer science expert, they may not that familiar with that very difficult computing skills that in TensorFlow, because TensorFlow is engineering masterpiece. So it has a very I won't say complicated. It is a little bit complicated, but it has a very beautiful structure. It hides a lot of different things. So it is not that straightforward if you want to translate a mathematical formula or algorithm into the code. However, PyTorch at least initially, it takes a different approach. It is very straightforward. So I think that probably contributed to the popularity of PyTorch a lot. That's why it built up a huge ecosystem. And another way to see the ecosystem is that because it already has a huge ecosystem built around it, so it cannot lose because people rely on this ecosystem. It is not just PyTorch alone. It is not about PyTorch anymore. I mean, at the beginning, it is about PyTorch, the difference between PyTorch and TensorFlow. But after the ecosystem has been built, it is about the ecosystem. Because you can see the PyTorch and the TensorFlow evolve to be alike each other. At the beginning, TensorFlow is more like a static graph, since you have to declare the computational graph before, and after that you execute the graph. So it is more like a lazy evaluation things. But PyTorch is more like a greedy, or you just run it when you write the command. When you execute the command, it just run at once. So it is easier to understand. So initially they are kind of different. One is eager execution and the other is lazy execution. TensorFlow is the lazy one and the PyTorch is the eager one. But after like TensorFlow 2.0 and the PyTorch 2.0, after these versions, they get much similar to each other. So, however, the ecosystem around the PyTorch has been built. So after that, it is not about the framework itself. Although they still matter, but I think the most important is the ecosystem. So that's why we were going to not only introduce PyTorch itself, we're introducing the ecosystem around it. Here are some key features and the capabilities that listed in the PyTorch official website, you can see that I circle out the robust ecosystem because I think this is the key features that the PyTorch currently empowered with. Also, originally, the people one of the strengths of the TensorFlow is the production ready things, because TensorFlow is more production ready, and the PyTorch seems to be more like a research oriented framework. But right now, it has a lot of abilities for production because its popularity, like I say, it has a robust ecosystem, a huge ecosystem. So people will building things around a PyTorch, including to deploy it to make it more production ready. Okay, so I think that's why it is listed in at the first feature that in the official website, and also because the models is getting huge and huger, bigger and bigger. So distributed training is one of the important things that people may be care about, and also it has some cloud support. Okay, if you want to install PyTorch or any other software, open source software, I would recommend the official official introduction to official guide to how to install it, because a lot of people tend to use Google or other search engine to search how to install something, and you may see some blog posts or like articles to teach you how to do that. Those are second-hand information. I recommend the official installation guide. The reason is that the reason that you might want to search the guide of installation is probably because it is difficult, or you have some trouble to install the software. So that means this software might be a little bit complicated and have some dependency. This situation applied to the PyTorch, because PyTorch depends on different backend engine like CUDA, or maybe had ROCm, that is for AMD CPUs. AMD GPUs. CUDA is for NVIDIA GPUs, and it also has CPU. Backend, and you can install it in different ways to do that. So it has many different dependency. NVIDIA is one of the things that causes a headache, because CUDA, you can actually install different version of CUDA on the same machine, and actually the CUDA also depends on the NVIDIA driver. So it is really a complicated system. Let alone the CUDA itself is not enough to support the PyTorch, because you still need like CODNN and a lot of different library built around the CUDA system. So it is difficult to install everything perfectly. If you just look at some blog posts or some articles, they may not update regularly, and they may have some strange approach of getting things, everything just work. So like CUDA may be installed in a different path, or the PyTorch may be installed in a different version. So instead, you should just look at the official guide of installation, because the software may get updated, so the article, the blog post may be get outdated. And even if it is not outdated, suppose you are just install them in a different way. I have encountered this situation a lot. People install the PyTorch, just look at some blog post, and they installed it on the system, and it didn't work. It can make it very, very difficult to debug. For many times, it turns out, the quickest way to solve the installation issue is just I installed it in a different environment. I create a new conda environment to start with these steps, because people do a lot of different steps, so the system has been messed around. It is very difficult to fix the issue. However, if you just follow the official guide, if you have some issues, people may already complain about it, and the official site will solve it because you follow the official guide. And if it didn't work, they have to fix it, because this is the official way to install it. So anyway, this is very important. If you want to install some software, just follow the official guide to install it. There are other ways to do that, but just follow the official way to do that. And here is a list of a document that listed in the official website. One of them is a get started. This is follow the learn section. Get started tutorials, learn basics, PyTorch recipes, and intro to PyTorch. This is a YouTube series. So there are a lot of materials that help you to learn the PyTorch. So that's why I am not providing a beginner's tutorial, because there are already a lot of beginner's tutorials. And as I mentioned before, you should follow the official one, because the software is getting updated regularly, frequently. So any materials that is not updated frequently will be outdated. And the official site will get updated frequently. Another thing is a document. One of it is a PyTorch document, and the other is PyTorch domains. This can be seen as, you can see that I use red pen to circle it, because this indicates the ecosystem around PyTorch. Because PyTorch domains means the libraries and frameworks that is domain specific. We'll see that a little bit later. These things including like PyTorch video, PyTorch audio, PyTorch image, type of torch vision. Torch vision, and it's like a reinforced learning, something like that. Okay, let's begin with the data pipeline of the PyTorch. PyTorch has a data pipeline. There are two major parts of the data pipeline. One is the data loader, and the other is the data set. So for example, you can use datasets to, this dataset is from the Torch Vision, but it has a dataset in the core Torch PyTorch system. They work similarly, but one of the benefits is it has some common dataset available. So you can use it easily, like dataset.fashionMNist, and to get the data without to download it by yourself to pre-process or to parse the data file. It will make the dataset automatically. And after you have a dataset, you will get a data loader to wrap around the dataset. Data loader is more like a iterator. So you can see that I can loop into the data loader. So the training data is a dataset object, and I wrap it around the data loader. There are two things that data loader does here. There are a lot of things data loader do, but two most apparent things that data loader does here is that one of it makes it like a mini batches. So instead loop over a single element one by one, it loops a batch, one batch, and batch by batch. The other thing is it becomes things like an iterator. So that's two major features or characteristics of the data loader. And also it can handle things like the payload data loading and prefetching, all these kind of things. So just to be complete, in case that you haven't seen what PyTorch is, this is a simple example of how to define the neural networks by using PyTorch. You simply define all the layers, right? Like here, the linear, railroad, linear here. This is a sequential. The object in the PyTorch to represent a model or a layer is called the module. So we're subclassing nn.module to define a network. In it, we initialize these layers because these layers has some weights. So there are some states that need to be stored. So we have to initialize them to declare them at the beginning. And the forward is the part for logic. How does the network works? You can define these layers in any order, but the forward is the logic or the flow of how the networks run. And you can simply do things like create an instance, a model instance right here, and you can move this model to the CUDA or other device as well. Another thing that happens a lot, like 4 or 5 years ago, is that people come from TensorFlow background. In TensorFlow or in Keras, you can use model.summary to get a summary of the network, but it doesn't have the same functionalities in PyTorch because PyTorch doesn't have a model.summaries. So people get a little bit confused. But in fact, it is even easier in PyTorch to see the contents of model. You simply print the model. You can get the information of the model easily, pretty much like the summary. However, because in Keras or like in the Keras is more like a lazy approach for defining the neural network. So the declare part and the logical part you are doing it at once. So when you do the declaration, you also declare, not only you declare which layer or weight, and you also define the network flow at the same time. So in Keras, the model.summary, you can get the whole you can get the layers, and you can also get the network flow, how the network works in your summaries. But in PyTorch, because the logic or network flow is defined in a programmatic way, it is difficult to kind of showing it in a graph notation. So this one only shows which layer is contained in this model. So that's the differences. Okay, so talk about dataset. I think a lot of you might, in 5 or 4 years ago, people may kind of overlook the data pipeline. But right now, I think because of the official documentary, it's also start with the datasets and the data load, data pipelines. So people are getting notice to these tools. But there might still something you might miss with this dataset object. One thing is that there are 2 types of dataset. So the first type is the map style dataset, which is probably the dataset type you will encounter most of the time. If you only know one type of the dataset, this is probably the type you're familiar with. So what is the map style dataset? Basically, it is a special kind. It is just a kind of like a list, a Python list object. If you want to make a customized dataset, you only need 2 things. The one thing is you only want to override 2 methods to implement 2 methods. One is the length. So you think about the dataset is like a list. So a list has a length. So you need to provide the information of, okay, how many samples are in this dataset. So that's one thing. You need to provide this information. It is usually the easier one. The other one is the get item. That is, you need to tell, people can ask you which is the first sample in this dataset. What is the second sample in this dataset? What is the third one? What is the fourth one? And so on. So if the length is 100, so people you should return all the sample from the 0 for index 0 to index 99. That's 100 different samples in total. So that's all. You only need to implement 2 methods. One is the length of the dataset, and if people are giving you a given arbitrary index number between the 0 and the size of the dataset -1, you should provide the samples, return the samples. The format of samples is mostly free. It is free form. You can return anything. However, in the training loop, the model usually expect that we have a tensor layer. So, but you can use the transform. Because the dataset supports some transform, you can use some transform to finally make it to be a tensor. So if you don't use any other transformations or other things, like here, you should return something like a tensor, a list of tensor, or actually a tuple of tensors. That's the most scenario. So defining a customer map style dataset is easier. It's easy. You simply provide the information of how many samples are in the dataset, and you just number the samples from 0 to by numbers 0, 1, 2, 3, and when given arbitrary index number, you simply return the sample, and preferably it is returned in a tensor form. when I say tensor, I mean PyTorch tensor, a tensor object. So that's a map style dataset. The other style is the, I didn't write the name right here, but I probably should. The other style is iterable style, iterator style. It is arguably even easier. You only need to you're subclassing the iterable dataset instead. In the custom dataset, you subclass the dataset, but in the iterator style, you're subclassing the iterable dataset here, and there are only one method you need to override or implement. That is the iter magic method here. It is just like the implementation of other iterator. You simply return the items. You simply return the iterators that iterate over all the samples. You can see that it is like here. It simply return an iterator that is ranged from the iterator start to the iterator end. In the middle of this function, this method seems to be a little bit complicated because it is a demonstration or illustration for the case that you need to handle how the multi-process or multi-worker scenario. You have to handle it by yourself. The data loader supports both the iterable dataset and the map style dataset. However, there are some functionalities supports only the map style dataset. Because the logic is that the most logic for handling the dataset like multi-processing, multi-worker, or like shuffle should be handled inside the iterable dataset. But the map style dataset is kind of like a list. It's more like a static dataset. It's just a list of data. It is more static. So the dynamic handling, like shuffling or like assign it to different workers, all these kind of things can be done in data loader. However, in the approach when you're using the iterable dataset, you have the full control, but you have to do everything like shuffling or assign the workload to each different workers. All these logic things you have done by yourself. It may be a little bit tedious, but on the other hand, you have a full control. So if you really want to customize your dataset and you are not familiar with the tools provided by the PyTorch data pipeline, then you can. But if you are familiar with coding, like in Python, you can choose to use iterable dataset and handle everything by yourself, like the random shuffling and like weighted sampling. You can do a lot of different things like this one. So for example, if you have imbalanced data, you want to have some strange specified algorithm to make the samples to be more even, like a dynamic adjust the ratio of the positive or negative samples, all this kind of thing. Then you can implement it in the iterable dataset. You can achieve anything you want without knowing too much about the PyTorch. So this is one of the benefits that I think that I mentioned that the PyTorch has, is that even if you are not familiar with the tools, you can still do it in your own way. It may not be the perfect way, the best way to do so. It may not be the best practice, may not be the shortest implementation, but at least you can do that. And sometimes for people doing research, doing experiment, it may just good enough because it's just one-time thing. You're doing experiment, you're training something, you want to solve the issue of imbalanced data. If you are using something like more like it is designed very well and very elegant. I'm not saying this cannot be achieved in TensorFlow. You can still do that, but it will be maybe a little bit difficult because TensorFlow is more. TensorFlow also have a data pipeline. It is designed very well, but it provides a lot of different tools. But because you can still work with it with a lot of different things, kind of like this. If you understand the principle, how the data loader or data pipeline in TensorFlow, how it works, you can still do a lot of things like this one. But in PyTorch, it actually kind of encourages you to do things like this one. So even with the map style dataset, because the get item is what you can customize, if you really want to shuffle it inside the get item, you can still do it. It's just not recommended, but you can still do that. So after people familiar with these kind of things, and they are getting familiar with PyTorch, they probably will eventually doing it in the most correct way. But I think this is the personality, or I won't say it's a feature or capability, but this is the characteristic of PyTorch that why people love it. And I can see why people love it because of you can just mess around it and it just works. And another object in the data pipeline is the data loader. So data loader is a customizable iterator. So for the case for iteratable dataset, the data load didn't make much sense, except making it to be from a sample by sample to a batch by batch iteration. So it still works for the iterable dataset, but I think the primary functionality is to make things from iterated from single sample to iterated over batches. I think that's the most function for the iterable dataset. However, for the map style dataset, the data loader is a customizable iterator. You can customize it in many ways, like you can do the prefetch, do the shuffling, whether or not we should, if we are doing the batching, whether we not we should discard the last batch, because the last batch is maybe is not a full batch. Suppose we have a batch size like 100, and your dataset has a size like 742. So for the last batch, each batch should have 100 samples, but for the last batch, it will have 42 samples. So that 42 samples will behave differently, treated differently than the batches before. for one thing, the loss is average for these 42 things instead of for the 100 things. It may even affect for the convergibilities. So you may want to discard this 42. So you can decide whether or not you want to discard the last 42 elements. You can customize this iterator. So data loader is just a customizable iterator. It in fact has you can use ITER, you can see here, ITER train loader to get the actual iterator. Most of the time, we are just using the iterator itself. So you can see the train data loader is essentially an iterator builder. So every time you loop through the data loader, like what you do, like here, behind the scenes, it uses ITER to control an iterator. So here, you control a new object called the iterator and loop through it. So you can see that if we break right here, the iterator is may still alive. So it will cost some resource like a memory, or maybe even in cooldown memories. So this need to be very careful. When you loop through the data loader, it will construct an iterator for you. So sometimes people construct the iterator specifically, like here. Okay, here. Control the iterator specifically. So we can break here and rerun the iterator again. Sometimes we do that to control the memory or things. And you can delete the iterator manually to make sure it is deleted. One thing that helps you to customize your data loader is the sampler. So sampler is one of the key component of the data loader, especially for the, specifically for the map style dataset, because it is how you sample the data. So all functionality like shuffling or batching can be done in the sampler. There are some simple sampler class. This is the base class. You can customize your sampler by subclassing the sampler class, and also it already provides some useful sampler like weighted random sampler or distributed sampler or like subset random sampler. What is subset random sampler? One useful scenario is that if you have a huge dataset, like 10 million samples, and you don't want your one epoch to be run like 2 days, then you can use subset random sampler to actually just sample a subset. That happens a lot because when we do some project, people may collect data more and more data. So originally you have designed a training routine that works just well. But after a while, when you collect more and more data, you have like 10-fold of data, 10 times of data than the original one. Your original training routine does not work because each epoch has actually 10 times more samples. That breaks your training routines, because you have already kind of adjusting or fine-tuning your tuning or training routine to work very well for the original data. But after you get more and more data, the training routine breaks, just because each epoch have much more steps than the original one. So how to fix it? One thing is that for each epoch, you simply sampling just part of the dataset instead of the whole dataset. So suppose originally you have only like 10,000 samples in your dataset, and after a while, you have designed your training routine for the 10,000 samples, and after a while you have collect like 10 million samples. Instead of just increasing your data and do the same routine, which will definitely break your training routine and making it running like longer and longer time, like it doesn't even finish. Instead of that, for each epoch you use like a sampler to just sampling like 10,000 samples from 10 million samples, and it should work just well. And because you are sampling from a bigger distribution, it may solve some issues like overfitting, but still keep your original training routine works. You don't need to change your learning rate or batch size or other things. It should just work just as well as the original one. The other scenario is you have imbalanced data. So you might want to make it more balanced and in a more customized way. Sometimes to deal with imbalanced data, you're not making every category samples to have equal chance to choose them. Sometimes you even want to when you do the training, you want to have even more chance, more than the average chance to choose the minor class. Sometimes you want to do that. Then by using a weighted random sample, you can assign the weight of each sample. So by adjusting the weight of the minor class and the major class or other class, you can actually arbitrarily you can adjust the ratio of how likely each class has been chosen in any way you want. And also, you can also assign the number of samples here to solve the issue that we mentioned before, that the dataset too large issue. So by setting the numbers to be like 10,000, each epoch will contain only 10,000 samples to train. And you can compare your training result to the original one, like when you have only 10,000 samples, because they are more comparable. If one epoch has like 10,000 steps, I mean 1 million steps, 1 million steps, and the other only has like 1,000 steps, they are not comparable epoch by epoch, because one has too many steps and one have only just like 1,000 steps. They are not comparable. So if you want to compare them to each other, you have to make sure that each epoch have roughly the same size. This sampler is your tools to help you do that. It also has a distributed sampler to simplify your work if you have multi GPU or multi machine training. When doing a multi-processing data loading, it will have you can assign a number of works to accelerate your data loading. Because a lot of time the bottleneck of training is the data loading, especially if you want to load your data from a hard drive or a network. And Python is not very good for multi-threading. So it will use multi-process to do that. And Python multiprocess is a headache. So will give you a lot of headache. So just be careful about it. I didn't put it right here. Okay. The multiprocess, let me see. Okay, I put it in the 2 slides after this one. When you do a multiprocessing, one thing you need to notify is that it is not recommended to return CUDA tensors in multiprocess loading. So that's one thing you need to be very careful about multiprocessing. You can check it and see the detailed reasons, but just realize that multiprocessing is a very complicated issue. The works rely on Python's multiprocessing. Python has a module called a module in a standard library called multiprocess. So it has a different mode for multiprocessing, like spawn, fork. I think it also has a fork server or spawn server, things like that. Okay, so the two most common one is the fork and the spawn. The difference between fork and spawn is like you just run the same program again. So it is a totally independent program, but has the same code. The memory space are totally independent to each other. So in order to make it more like multi-thread or like cooperate to each other, you have to send the data from the main process to the sub processes. Because you spawn them, they are just running the same code. They know they have the same code, but they are different, totally different process, totally different execution. So they have totally different data than yours. So either they are constructing the things from beginning, or you have to send the data to them. So in the data loader case, you have to send the data from the main process to the subprocesses. And in Windows and the Mac OS, they are using Spawn because this is a more popular or more easier one, more common one, like the common factor between different operating or platform. So they are using Spawn. And it actually using some kind of pickle serialization to send in data from the main process to the workers. So if something is not serializable, it's not a pickle serializable, you will get in some trouble. So you have to understand the differences. It relies on the pickle serialization. So everything in the dataset has to be serialized using pickle. So that's how it works. But in the Linux, it uses fork. What is fork? Fork is also a different. You are still running the code in a different process, so it still have a different memory space. However, the memory space is copied, is cloned from the original one when you fork the things. So you have the idea is you have a main process here, and if you fork the subprocess here, the subprocess will have the memory of the original one. When it is getting forked, it is going to run a different subprocess for sure, but it will share the same data. However, the memory model is that in the logic, everything is cloned, is copied, is cloned. So they have separate different memory space. everything is cloned. But because we wish to save the memories, so although the logic that the memory is just copied, but in practice, we are using an algorithm called the copy on write things. That is, in fact, the memories are not actually copied. But because they are not changed, if they are not changed, it doesn't matter, right? But if some process, even either the the main process or the sub process, if they are writing things to the memory, then logically they are different. So at that moment, the memory is getting copied. If something is getting write down, the memory is getting copied. So logically or theoretically, the subprocess and the main process feels like they have their own memory space. It's just they are copied when they are getting forked. But in practice, if the memory has not altered or write it, then they kind of just using they share the same memory address. But after they are altered or adjust or copied or write it, then at that moment we will separate that part of memory and make a copy for the subprocess. So that is we are using actually copy on write algorithm for multiprocessing. So that makes some issues that because Python has the lock and has like a counter, because the memory management use a counter to mark the memory. So sometimes, so for some object, they are going to write very frequently. So they are going to copy, so they will cause a lot of memory. So there are some issues we need to be considered about to save the memory to make it more efficient. And a lot of detail is handled by, in many cases, it is handled automatically by the data loader and by the Python, like PyTorch, NumPy, to make sure that memory is not that frequently write. So at least for a large array or large tensor, they are going to share them, so make it more efficient. But sometimes, if you are doing something funny or you want to try something more tricky, it may cause the memory to be cloned or copied. So it will, if you have like 2 or 3 workers, it will have a huge memory usage. So you have to need to be kind of take care about, keep an eye on these potential issues when you use multi-workers. So that's what works behind the data works. They really work rely on the Python multiprocessing module. Personally, I think multiprocessing module works just fine if you know how it works, but I want not to just I will still not be, also be very careful whenever the multiprocessing module is used, because they are they are a thing that will cause a lot of potential issues. Okay, so this is how you build a neural network. You just submoduling the NN module and has a forward to implement the logic and use the init to initialize the weights, to declare the weights. You can easily get the model parameters. Not only you want to have access to it, a lot of like the optimizer also has to query the information about the what parameters are in the what trainable parameters are in this module, in this model. So you definitely can get the information from the model. Otherwise, it is impossible to implement the optimizers. So this is how you get the information. So one thing that is core or fundamental to the PyTorch core is the automatic differentiation. So here is an idea how it works, and it is easy to understand. And as we kind of inversed before, this is probably one of the parts that people like the PyTorch because it exposes the very fundamental part so that you can mess around with it, and maybe you are going to write a very long ugly code, but it is easy to mess around with it. So here's a simple example. Essentially, it's just W times X plus B, like what we do for a linear regression, kind of what we do for a linear regression. But this example is simply for the logistic regression, because we are using a loss function that is cross entropy with logits. So the sigmoid part is done inside the loss function. Okay, so basically we have an X and a Y. These are data, input and expected output, the target. And we have a W, which is a random initialized weight, and a B for bias. So we compute Wx plus B is equal to Z. Then we compute the cross entropy loss with logits. That is, we apply the sigmoid on Z and compute the loss right here. It can be visualized as this graph. This is X and we have a W. This W and B are parameters. So W times X and plus B, we get Z and get the user cross entropy. Cross entropy takes two inputs, Z and Y, and we get a loss. When we get a loss, we can use backpropagation to find the differentiation, the gradient of W and B by reverse the direction of arrow. So when we find the loss, because we want to minimize the loss, we have a gradient of the loss, the differentiation of the loss, the derivative of the loss towards 0, downwards to okay, and we compute the gradient of the loss. So the negative of a gradient is the direction towards 0. We can backprogram this gradient back to find the gradient of Z and find the gradient of B and find the gradient of W. That's how it works. But for a computation, it looks like a graph. The difference between TensorFlow and PyTorch is when we originally TensorFlow, the way TensorFlow works is that we define the graph at once. Then we execute the graph. And in PyTorch, it is more like, okay, when we define X, we compute the value of X. When we define Y, we compute the value of Y. And then when we define a W, we compute the value of a W. And in this line, we compute the value of B. So we define here. And here, we compute the W times X here first and plus the result to the B. So we run it one by one. So that's called the eager execution. And for lazy execution, we define the graph at once and compute it at once. That's the differences. So after we define the computer forward process, we record everything that is necessary for computing the gradients using back propagation. So default, we need because we are going to compute the gradient using back propagation. So when we do the forward computation things, at every step, at every function, it records the necessary informations needed to compute the gradient using back propagations. So it requires memory. The memory is as much as the memories of W. So if you are going to use back propagation, then you probably will need double memory usage, around roughly double memory usage, comparing to the if you want to compute the feed-forward process alone. Okay, so the thing how the PyTorch work for back propagation is you simply, because this is the start point of the back propagation, so we use last dot backward. It will compute the back propagation for all the gradients at this step. So it kind of working recursively and backwardly, what we did for the forward process. After that, the gradient of W and the gradient of B are computed. So you have every detail to implement your own optimizer, even if you don't know if you don't know any optimizer, the name of any optimizer like SGD or like Adam, you can already implement training loop if you know the basic things like this like metric multiplication. Even if you don't know things like data loader, data set, all this is you need. You can use all these operators and this pattern and the dot backward and gradient things to implement your your training routine, like doing the classification in the MNIST dataset. You're simple like using logistic regression. So that's the coding style or the personalities or characteristics of PyTorch. It exposes very detailed things, very low level things to you, but you can still use these low level things. It is not that low level. It is low level in the mathematical sense, but not low level in the machine code, like a coding sense. So you can use this if you are familiar with mathematics or computer science theories. It already provide the basic building fundamental building blocks for you to construct your own training routines to implement your algorithm. So as we mentioned before, back propagation requires memory usage. So sometimes we don't want them. So one way to do that is use with torch no grade. So it won't store the information that required for back propagation. So you are saving memories in the code that you are unable to do the back propagation to do the backward operator. If you are running the backwards on this guy, you are getting an error. You are getting an error immediately. And you'll get the information of how this is going to compute by getting the required grade property. Originally, it will have a true value for this property, but if you are using no grade, it will have false on this require squared property. Another way to do that is you can detach it, then it will also has a false value on the requires squared property. If you are working on a notebook environment, it may be more convenient to use these guys in a global space to manually turn on the gradient or no gradient. There is a function to do that. So you can use, so in fact, you can use a command that is turn on the gradient. I forget the name, or maybe you can just use a torch no gradient. I sort of forget the name, but there are functions that you can use without in a context. You simply in a cell, you just run that torch that like no grade things, and it will turn off the grade globally. And when you want to turn on it again, there's another function to do that. But most of the case, this one works just well. But sometimes if you're working in notebooks, or maybe you have already known that every operators in these notebooks is for evaluation, or there is a function that helps you to turn off it totally, turn off the gradient totally. Okay. So after we get the gradient, we can do the optimization. There are already a lot of functions already defined to help you to a lot of algorithms to implement some algorithms to do the optimization, like stochastic gradient descent or ADAM. So you can use torch.optim.something to get your optimizer and run the training loop. Also, this is a typical way to do the training for the PyTorch. The train loop and the test loop are just functions that you don't actually need these two guys. This is some just functions that you define by yourself for convenience, for easier to manage. So what is the train loop? The train loop is like right here. You get a data loader and a model and the loss function and the optimizer. So your train loop is look like this one. You simply loop through the data set. Okay, before that, you switch your model to the training mode. As you will see that there were evaluation mode when we do the test loop. What is the difference between evaluation mode and without gradient, with no gradient? The evaluation mode or training mode is to adjust the randomness inside the mode, or some behavior in some layer, mostly for the batch normalization and the dropout layer. But it also works as well as other regularization layers. But typically, the most iconic things are batch normalization and dropout. In the training, dropout will drop out some part of the neuron. But usually, when we do the prediction or inference, we are using all the neurons and kind of average them together, kind of like an ensemble model. So the dropout model works. The behavior of dropout model is different in training phase and in the evaluation phase. So by using this dot evaluation, we are turning the dropout layer and all other layers to in evaluation mode. The other thing is the batch normalization, because in the batch normalization, it will compute the mean and the standard deviation of the layer at runtime. But when you do the inference, there might not be a batch because sometimes you want to inference on one sample, and sometimes your batch size may be different than the training one. So it is not a good idea to. Sometimes it is a good idea, but in many situations, or in typical situations, we are not using the runtime statistic. Instead, we are collecting the mean and the standard deviation statistics when we do the training, and save them in the model. So when in the evaluation models, we are using that stored information, stored mean, the mean, the average mean, and the average standard deviation, instead of running the statistics on the input. So the evaluation mode doing that. However, it has nothing to do with the gradient things, like the storing the information required for a gradient. It has nothing to do with that. This is done by no-grade. So using no-grade to control whether or not to store information requires for backpropagation, and using EVL to control the behavior of layers. You can actually control the behaviors of a different layer independently. You just choose that layer and make that layer to be eval or not. And sometimes we need this behavior. I mean, we need a training behavior when we do the inference. Like for instance, in some game models, we probably still need the batch to do those, to make sure that they behave the same when they in the training. Sometimes we do that. So you can have full control of the behavior. So just remember, the eval or the train is for the layer behavior, and the no-grade is for whether or not you want to store more information for backpropagation. Okay, so for the training loop, we loop through the data loader. As we said before, data loader is just a iterator builder. So in here, it will build an iterator for this loop, and we get x and y from this data loader, and we are sending this x to the model. Sometimes we use x to device to model that device, so that we can actually move the x to the same device as the model. And then we compute the loss function to get the loss. Then we use the loss backward to get everything that the gradient of every parameters. Then we use optimize that step. Okay, we use optimize that step to run one step of optimization. And finally, we use optimize dot zero grade to clear all the gradient information that is stored. If you don't do that, and if you run the loss, if you run the new loss and run the loss backward, the gradient will be accumulated to every parameters. Sometimes it is the desired behavior, because for instance, if we are running a large batch, we want to run a large batch, but the memory size is not enough for that, for this kind of batch, like 32. If suppose we want the base size to be 1000, but we can only run like 100 for each time. Then we run then we make the base size to be 100 and run this 10 times. The loss back to compute the loss for the first one and compute the loss backwards, this 10 times. And then we run the optimizer steps So this effectively, logically, it is like running a batch size of 1000, because every time you run the loss backward, the gradient is accumulated. So logically, it is like running a batch size of 1000, but of course it probably takes more time because you have to run it like 10 loops, and after that you run the optimize that little grade, you get another round of 10 batches. So that's one way to do that. But little grade is you have to do that to make sure you compute you don't have the previous memory of the gradient. You can do that before computing the model, or before you're computing the loss backward, or after it, because it is a new run. So for test loop, it just compute some matrix right here, and it still loops through the data loader. You can do it manually. Everything, there's no magic right here. If you want to compute the running average, you want to do the average of, and the base size is different. Like we say, if you have a data size of like 742, and your batch size is 100. So for the last batch, you will have only 42 elements, and for the other 7 batches, you will have element of 100 for each batches. If you are computing the average over the 742, you have to be very careful. If you compute the mean of every batch, you have 8 batches and 8 means. And if you compute the mean of these 8 batches, you will not get the correct mean of the samples, because the last one only contains 42 elements. This is kind of unfair to other batches. There's no metrics to do that. You have to deal with these issues. You may just compute the sum of each one and add them together and divide them by the size of the dataset. And that's one way to do that. But in this case, you have to be very careful because if you are working on a 4-point and working on a very large dataset, it may be a little bit you may be worried about the accuracy or precision of the floating point, because if the sum is already a very huge number, the last few, like if you have a 1 trillion, if your number is 1 trillion, if you add 1 into it, it may not even in the precision of the floating number. So it will as well as add 0 into it. So there are a lot of issues about the computations, about the numerical things you need to worry about. You have to deal with yourself. There's no magic about it. Every possible difficulty is still there. You have to overcome to deal with them. So that's why we probably want better tools like I'm using Lightning and using the Lightning torch matrix that's provided by Lightning, which we will mention it later in this lecture. Or if you are using Keras, it will help you to do a lot of things easily. So that's it, probably that the TensorFlow's approach, it's wrapped or packaged everything in a very neat way, because of course we know that we can do that and the formula is not difficult, but implementation is usually difficult. And people may not even notice there are some difficulty. But because people didn't know that, didn't aware of the difficulty of those things, they are not appreciate with the complicated or elegant design or all these kind of things. This one is more accessible to the general public. general public researcher or scientist. So I think this one is still the best approach, because even though you have to deal with these things by yourself, as a researcher or scientist, you will eventually notice about these kind of things, and because it is more accessible, you have a chance to actually fix these things. Okay, another feature that is important is that you can save the models to serialize the models. The format is usually the PTH, PyTorch things. Maybe PyTorch. I never know what the PTH stands for, but the thing is, the typical way to do that is you save the state dict. The torch save is pretty much just a pickle. It handles some situations, but it just saves everything into a pickle. At least in PyTorch it do. So there's no magic or no. A lot of things you have to handle it by yourself, because the file name, the format is pretty much just a pickle. So you don't. Although this one is a typical way to do that, there's nothing prevent you to save different things. So you may encounter some people using a more funny way or strange way to do the serialization, and you may have a difficulty to load the model. But the typical way is this one. And also, it inherits the issues of the pickle, because pickle has a lot of issues. I will talk a little bit about it in next slides, but you can see that here. Okay, maybe in these slides we'll talk about it. The first thing is that because it only store the state of the model, not the model itself. So you need to have the full code of model. If you want to use these saved weights, you need to control the model. It is empty model. It has a random weights, or it doesn't have any meaningful weights. But you can load the weights from it. But anyway, you cannot use the weights without the model itself. So suppose if you modify the code of this model, it happens a lot if you want to change the code, modify the model. The code. Sometimes if you forget about the code about which code you were using to save this weight, you may have a difficulty to load this model, because it requires exactly the same models here to load this model, and you have to run the code. If you have some commercial considerations, that is, you don't want to provide the code itself because the code has some logic inside it. If you are willing to provide the binary weights to people, but you are not feel comfortable to provide the whole code inside to the people. This may have some issues, because you will have to load the code here before you load the weight. And another issue is sometimes you forget which model is used for this weights. Maybe VGG 19 or VGG 16, or maybe ResNet. You just forget what it is. You can still look inside the model to figure out which one it is. But sometimes the difference is just you have a more dropout layer or more batch normalization. You just change the activation function or things like that. It will be difficult to find out which model it is. So that's the issue. But this one is a typical way. people typically use this method to store their weights of the model. Another way to do that is you can torch save the model itself, because it basically just the pickle. But a lot of time you want to find the pre-trained weight, chances are you are going to find that is stored in the state dictionary. But in fact, torch is just saved since in pickle format, relies on pickle a lot. So you can actually use a model here to save your model, and you just load the model. And you have to set the weights only to be false. However, I mean, it solves one issue that you forget which model it is because it stores the model information. However, because it is a pickle, you still need to load the model before, load the code of the models before you load the model, because pickle will call the code, the Python code there to construct to do the construction. So you still have to run the code of the model with the same name. So it didn't solve the issues that if you accidentally modify the code and forget to use Git to save the checkpoint, or you just didn't remember which part has been modified, or things like that. And another issue of that is for a commercial scenario, it doesn't solve the case. There are other tools to do that, but I'm just saying that it is pickle. It's just pickle, and there's no magic inside it. There's no magic. It's just pickle. So you still have to have the code with you. When you try to save the checkpoint, you can. In fact, it can save a dictionary, because it can save a dictionary. So you can save the model state dict, and you can also save the optimizer dict, and you can save other information in a dictionary as well. And when you simply load it, you simply load the state the checkpoint, because it is just a pickle. It is just a pickle, so it's just a serialization. So you simply give it a dictionary, and it loads a dictionary. So checkpoint is a dictionary. There's no magic here, the model static, because you call it a model static. You can just call it a model state. You can call it a model. You can call it state 1, state 2, any name you want. It's just a dictionary. So you simply load the dictionary here and in here. This one is a usual pattern for the checkpoint saving in PyTorch. There's also one important thing is how to deploy the PyTorch models in production. Because we are in a school right now, and most of you are just students. All of you are students, but so you probably didn't worry about the deploying things, how to deploy your model. You may not even aware this is an issue, because you know the PyTorch can do the inference, can do the training. So what else do we actually want? So one thing is about similar like the issue before. Sometimes we want to serialize everything in a file. Even though if we change the model, not only for the commercial scenario, you don't want to provide code to your user. Sometimes it is just for convenient, because the whole business logic is the same. You want to drop in, replace it with a new model. This new model may have a different architecture like a ResNet, or maybe it becomes a transformer model, but you want just replace one file and everything remains the same. And if you use the things like this one, this guy, you have to change your code. Sometimes we want to separate to decouple things, decouple the component of this application. So one thing is the like AI part. The AI part is probably, the deep learning model part. Then you want it to be in a simple file without changing other codes. Sometimes you want to do that. So need a format that does not require the model itself. But in PyTorch, it is kind of difficult because everything you can write in Python code. Python code is difficult to serialization, to serialize. Sometimes you still can serialize Python, but it may be too powerful. Sometimes you just want the graph, because the neural network model is kind of like a network flow. Sometimes you just want to store the network flow is enough. So one way to do that is to store it in a standard, mostly standard format, like UNCS, Open Neural Network Exchange format. It is an open standard format for representing machine learning models, mostly including, as the name suggests, neural network. And Torch has an UNCS module that provides API to capture a computation graph. So it has to capture the computation graph. It has to do something. We'll discuss it a little bit later, but PyTorch has the ability to transform the customized model or customized module or all those things, the logic, into graph. And because you have this ability, then we translate the graph into, that was a difficult part. The other part is that there are different standards between even for the statistical frozen graph, the computation graph, there are different standards. So you still need to convert the native graph representations into UNCS graph representations. And there will be some compatibility issues because some operators in UNCS is defined differently in the similar operator or the operator with the same name. They have different behavior or functionality in PyTorch. So that still have some difficulty and you need some optimizations. But at least that is doable. So one way to do that is UNCS. And the other is, okay, let me say this first. That after you export the model to the UNCS, you can run it with Microsoft's UNCS runtime. So sometimes you can actually run the model inside the C++ files, Rust, or in other language, not only in Python. If you are using Pico, you are limited to run it in Python. But if you are converted into UNCS runtime, you can run it in everywhere that supports UNCS runtime in other language. Of course, you can also run in Python, and it may be, chances are it will be running much faster than the original one. So this is how you do the UNCS convert. You first use the UNCS Dynamo export. Dynamo is another component of Torch to do to convert the Python PyTorch modules into a graph representation. So you use Torch UNCS Dynamo export to export everything into a UNCS program. And when you save into UNCS files, you can load it in using UNCS runtime. UNCS runtime has different issues because it has different version, and sometimes it's difficult to install. If you are sometimes it's easier. It's not always difficult to install, but sometimes you may encounter some trouble, like version complications or some things like that. but it is worse to install it because in many cases it will make your program, your model to run like 2 times faster. Sometimes lesser, sometimes doesn't even work, but sometimes it's 2 times faster or even faster. And you can use like Neutron or other tools to visualize the structure of a model, to visualize your model graph. Another similar thing is Torch TensorRT. And because UNCs used TensorRT as well. So I personally, my experience is their performance is roughly the same. So if you are using a TensorRT backend for UNCs, for our UNCs runtime, I will choose the UNCs runtime because it is more standard and the performance is roughly the same. In principle, because TensorRT does not need the compatibility with other, doesn't need to confirm the UNC standard, so it has more freedom to optimization. However, my experience is the UNCs with TensorRT backend works just as well as TensorRT itself, and installing TensorRT is another pain. I mean, install caused by installing TensorRT. If you are running a CPU backend or other backend, it may not be that trouble, but the most pain is in the TensorRT. So you can still insert Torch TensorRT as well. I mean, if you prefer it, but personally, I like the this UNCs runtime. I use UNCs runtime more. And a lot of models are provided in the UNCs format, so you can install UNCs runtime and install the TensorRT as a backend to have the full benefit of using TensorRT. Another component in the Torch to do the similar things is the Torch script, or that is Torch script. So one way to do that is use Torch JIT trace to trace your module. How it works, it works like it run this module like myself on this input. It will follow the step one by one, kind of like the things do the when we do the when we store the back propagation information, when we do the forward process. It is kind of like that. It runs the forward process and record every step and build the graph. So if your model have a if else, like a lot of branching, it may not trace that well because it has branching. But if it is not the case, it will do very well. And it is more easier to understand. Another way is use JIT script. It will analyze the source code of your model to build the graph. So if most of the time I'm using this one. And it works well. But you can imagine in some case the program you were writing is very difficult to understand by the analyzer. So it will have generate a wrong output, or even maybe it failed to generate an output. It is possible. But you have two choices. One is use the trace and one is use the script. In any case, you will have your trace cell, or you have a script cell. You have a script cell. Then this guy can be okay. This guy can be saved into a file. Sometimes you usually call a PT file. You call the PT file. And this PT file does not require you to have the module code loaded because it is already a different thing. You can load this one, and the loading module works. It is a different thing, but it works kind of like the original one. It is compiled and work like the original one. It lacks the ability of like if you want to do some modifications or like maybe like back progressions, it may not work. But if you do the inference, they are working just like what you should do. Just like what you do. Okay. Just like what you do for the normal PyTorch modules. And also, you can use the libtorch, library torch to actually load the models and run the models in C++ or in other language like Rust, C. However, the torch script is not actively developed anymore. It is not obsolete yet. And as official says, it is still supported in the foreseen future. It just because the torch is involved, PyTorch is involved in the PyTorch 2. So it has changed the development direction. And the torch script is kind of mature already. So it is more like it is in a maintain mode. It is not actively developed anymore. Instead, there is another approach called the Torch Dynamo. It is more like a graph-oriented things approach to the deep learning things. It's called a Torch Dynamo. It has a very fundamental change to the PyTorch, and it is more complicated than the original PyTorch behavior. So you can do things like torch compile here to compile this kind of thing, kind of like the in TensorFlow 2. It has a I actually forgot the name, like TensorFlow compile things, like pretty similar to that one. So it can compile this one to make it more efficient and more traceable. It is an optimized code here. It can do the to compile your functions and to actually get you a graph here. So this one is the thing that you can use torch compile to do things. Another component is torch serve. It is a kind of like a server, kind of like a model server for PyTorch. I didn't use it a lot, but I think it's kind of like the NVIDIA Triton. But NVIDIA Triton supports many different backend. So I use Triton more. But Torch serve is, I may be wrong, but in my experience, it's sort of like things. So if you are trying to serve Torch model, it will help you to manage your memory and the different models together. So it is easy to use to serving Python models in production. Another thing related to the deploying or production is XQTorch. It is used for edge device to deploy your models on edge devices. Usually we are using PyTorch mobile. I haven't used XQTorch, but I use PyTorch mobile a lot. And it is actually pretty fun and easy to use. if you use PyTorch mobile to develop your mobile application. I actually like it, but PyTorch mobile is based on Torch script. So it is like what we do for Torch script. It compile it into a graph, and there is a component already written like a light interpreter to interpret these things that you can use it on your mobile applications. So that is PyTorch mobile too. But XUTorch is another component that is more focused on the edge case deployment. So it will has more, it has even less memory footprint, and I'm not sure about the performance, but it is even performance wise or like memory usage wise, it is better, claimed to be a better alternative to the PyTorch mobile. So that is another thing in this ecosystem. And it also has some parallelism APIs, which is also very good for deploy and also for training, most of it for training. You can see that for training, but it also works for the inference. So distributed deployment is also a thing. So basically, we are introducing some fundamental parallelism models in PyTorch. One is called the DDP, the distributed data parallel. It usually called just a data parallel. I will see it in next few slides, but data parallel is simply you split your data. So suppose you have a batch of 1000 samples and you have 10 computers. Then we split the data like into 10 different batches, each have 100 samples, and we use each samples on each of the 10 computers. So that's called data parallel. We split the data into different computers, into different computer nodes, or maybe into different GPUs. And the other another thing is called the model parallel. That is, we separate the model into different parts. So there are different ways to do that. So one of the fully shared the data parallel training, and there are tensor parallel and the pipeline parallel. There's the fully explanation or description of what is FSDP, a fully shared data parallel, is in the PyTorch website. It is a common way to split things. And the tensor parallel and the pipeline parallel is a more advanced ones. So for a distributed data parallel, it's like we said, if your model fits in a single GPU, but you want to easily scale up your training using multiple GPUs, then you use distributed data parallel. So it's easy to choose. If your models can be fit into one GPU and you have many GPUs, then you can use this distributed data parallel. But if your model cannot fit into one GPU, you use FSDP. In most cases, we are just using these two guys. These two are the two I'm familiar with. I haven't used Tensor DP and Tensor Parallel and the data pipeline parallel yet. So most of my cases, I'm just using FSDP and the DDP. These two guys are just in most cases, you use these two guys. But if FSDP is not good enough for you, you can try to use Tensor Parallel or Pipeline Parallel. So they are more advanced choice that you can have. These four are the basic parallelism models in PyTorch. And PyTorch has a launcher called Torch Run. If you are training a lot of different parallelism, this is one of the popular approach. May not be the most popular one, but this torch run is widely used launcher. This is a fair statement. It is widely used. You can encounter it in many different training script or training routines in several different projects. It is one of the native one, is included in the PyTorch one, and it is widely used for distributed training. Another library that is used a lot is accelerated. It supports different backend, and it enables you to do the distributed inference or training. And it is also very popular. I'm not sure which one is popular, but I see a lot of things. Maybe my personal feeling is Accelerate is more popular because it can do, especially for inference. But I may get it wrong. But both of them are very widely used for sure. And I will introduce there's also DeepSpeed. It's also very popular for training. These are some domain libraries used in PyTorch. Okay, like Torch Vision, Torch Audio, Torch Text for text, Torch Rec for recommending systems. And there's also PyTorch 3D. You can do some 3D things like nerf or Gaussian spiraling or other things. If you like text to 3 models, it is suitable for all these cases. So the thing is that all of these things demonstrate that the PyTorch is so popular that a lot of domain specific people want to use in different domains, and they provide ready-to-use functions, ready-to-use models, fundamental models, or useful models for this area, like text, audio, and vision. Keras is like this. Keras also has Keras text language model, Keras language, Keras vision, Keras something like this one. So they are also heading the same direction. But I do think Torch in recent years, the Torch version are maintaining more comprehensive. Like in Torch Vision contains a lot of different like segmentation models, tracking models, already provide several very good models that you can already use, and I am kind of rely on them. And PyTorch 3D is another thing that it's more niche, but it's getting more popular and widely used. It only works on Linux. One thing that it only works on Linux, but it provides a lot of different useful functionalities. And there are also PyTorch videos. So not only it has Torch Vision, it also has PyTorch videos that help you to work with videos. I haven't used it, but you can imagine it contains some models, fundamental models, and utilities that help you to develop models for videos. And the firewall is for federated learning framework. The Colossal AI is for large-scale deep learning, for distributed systems, for parallelism. It is also kind of popular in many cases. And also DeepSpeed. I haven't used Colossal AI. I don't have much experience of Colossal AI, but a lot of trainings routines require you to use DeepSpeed across different GPU. So this one is also very popular for training, especially for large language models. I'm not sure it can work for other models, but yeah, I didn't remember if I have trained it for any like diffusion models, but it certainly works when you training like language models, you will encounter a lot of trainings require you to install DeepSpeed. And diffusers is a Hugging Face model like transformers. So it also works very well. And a lot of models are, I'm not sure if most models are PyTorch based, but at least whatever I used in the diffusers, they are all using PyTorch as backend. And a very popular module for PyTorch is InOps for Einstein notation, which we introduced in the NumPy Einstein notation. So you can actually construct your operations in PyTorch just writing the Einstein notation. Like we said, the inner product or matrix multiplication or like tensor dot, they have different generalization and a lot of subtle difference between several different usage. All of them have their place to use, but there are some subtle differences. And it is kind of difficult to figure out the difference between like the matrix product or dot product or things. Because sometimes they have similar name and the different meanings in different libraries. But if you are using Einstein notation, it is very clear what you actually means. So there's popular module available in PyTorch. And of course, there are PyTorch Lightning. That is what if we are going to see our example in homework, I'm using PyTorch Lightning as well. It's kind of like a Keras for PyTorch, but I think it is even lighter wrapper for the PyTorch, because the model you were writing, you're also using PyTorch. Mostly using PyTorch to write your model, and the PyTorch Lightning provides only the convenience tools for training, and callback for visualizations for seeing the matrix. And in fact, you can have a different level of fully controllable or more fully controlled toward the PyTorch side, and fully convenient toward the PyTorch Lightning side. You have different spectrum. You can do the different things. It's kind of like the Keras vs TensorFlow, but the TensorFlow part is probably more technical and controllable, and the Keras is arguably more, I think, a little bit more convenient than Lightning. So the spectrum is similar, but I think the Keras TensorFlow spectrum is a little bit wider, but they are pretty much heading towards the same direction. So here is a toy example for Lightning module. It pretty much just as the same as the you got a model for your PyTorch model you already defined. So for training, you just wrap it with like how do you compute the loss, and you do a configuration for optimizer. So here is a thing that so the Lightning module is actually, you can consider as a configuration of the training. It is just the configuration of the training, like the learning rate, the optimizer, and how you compute the loss. However, you can still wrap everything, define your module inside the Lightning module, kind of like the Lightning module as a module. You can still do that. But the correct logic about this one is it is a configuration of the training. And after you have already defined your Lightning module, you can still use the training loader and testing loader. The data loader from the PyTorch. Although the Lightning provide their data loader, their own data loader, their wrap of data loader, but you can still use the Torch data loader as well Then you define a trainer. The trainer is more like a hard description, like do you want many workers, or do you want to train it on CUDA or on other device? So the trainer is more like this guy, and the Lightning module is more like the more theoretical definition of the training, but the trainer itself is more hardware and platform specific. After that, you do the train.fit, then you can fit the module, just kind of like the scikit-learn or like Keras. You don't need to worry to write the training loop by yourself. You probably will think like, okay, it doesn't help much because I still need to write the train step, right? The difference is it is more like standardized. So a lot of tools can assume that you are writing in this way. So a lot of tools provided by Lightning can be easily used, including the torch matrix. A lot of time we want to implement a callback, like to see, okay, I want to see the precision or recall during the training process. It may be difficult to implement that, but in Lightning, they are just simple callback that you can easily monitor. And you can have a very pretty progressive bar to see the progress and seeing the matrix showing on the part. And it automatically has the TensorBoard integrations. So it has different logger background, like TensorBoard, it's naive, like a YAML or JSON background, William bias, so you can store your log to the cloud. A lot of different logger is supported by the PyTorch Lightning. So you can easily you have it is much more convenient than writing the PyTorch from scratch. Although it is not too difficult to do that, but if you are doing it a lot and you have to write it in a different way, I think Lightning hit a balance for customization and convenience. And another library is called Cortina. Cortina is like a computer vision library like OpenCV, but it integrates with PyTorch. So you can use a lot of computer vision functionalities inside the Torch library. For example, you can actually do a two-dimensional feature detection, like matching right here. And you can do the perspective transformation inside the PyTorch models or inside the transformer. Not the transformer, transform. When you do the data loader, since you can use the data transformations, you can do that. And it also has something like a geometric transformation, like here is a perspective transformation. This is kind of like a warp perspective. Although PyTorch has a warp, it has a general warp transformation, but Cortina provides more and more everything you think about the computer vision. I will just say everything. A lot of things you think about the computer vision you can find in Cortina. So that's beside it. If your target is just running the computer vision, it can use CUDA to run this kind of things. So it can be used in either way. One is to use in the computer vision domain to accelerate the things, the process, computer vision process. And then the other way is you can integrate the computer vision capabilities inside the PyTorch frameworks, PyTorch pipeline. Okay, so that's about the things. Then we are going to talk about the homework. We are going to talk about our next homework. So here's the course website here. Let's see. The homework is right here. Okay. This one should be homework 3, I guess. 2. Okay, 3. This is homework 3, not 4. Homework 3. So here's a description. Maybe you can read right here, but the thing is, you can easily see it in this picture. So at the beginning, we have a low resolution images. So you can plot this. I actually have a better slides, but I forget to provide right here. But if you see this one, you can see this as a scatter plot of the samples. Sort of like the decision boundaries. Let me check the like here. The red one is probably represent the white, and the purple one maybe you can consider as a black. So this one is similar to the case of this guy, or maybe we should put right here of this guy. So although we put it into square, you can consider it as just a scatter, the samples, and each white thing is just a white dot. So it is a dataset. You have two-dimensional feature x and y, and you have two colors, black and white. So you can do classification. You can actually do the classification, and finally you will get a graph like this one. Not the dash or the boundary, but you can have two regions. One is a purple region, and the other is a pink region, a red or pink region right here. Maybe more specifically like SPM thing here. Or like this one. You have different regions. Not this one, like this one. You have different regions. One region is here and the other is here. So the thing is, I'm asking, the homework is asking you to choose one of the choose one low resolution image, or maybe the resolution should be less than 64 by 64, and typically it should be sort of like 30 by 30, 20 by 30. It's a very low resolution images. You can find a lot of in the like 8-bit art things. Then you do the classification. You can use support vector machine or using PyTorch to construct a neural network to do the classification. And you draw the boundary. Then you will get something like this one. Kind of like a higher resolution, a super resolution image of this one. So for here, it is a resolution like maybe 24 by 24. And this one is a lot, maybe 300 by 300. And for here, this is an enlarged image as well, but should be something like 20 by 20. And I enlarge it to be 800 by 800 by using neural network. This is, if you get something like this one, it's not perfect, but, or maybe not even good, but it is okay. Because you can understand, okay, why this eye is not, it's disappeared. It's still there right here. But because our information given it here is white, it has no means to know that the white should separate the black here. So one way, if you want to do this really well, you can modify the dataset. Because the dataset, if you do it from very naively, you simply treat every dot as a sample. But if you do it more manually, by like, okay, if two white dots are linked together, like here, then maybe everything between these two white should be also white. If you do this one, then you will have a more enlarged dataset, and maybe you can solve the issues like here. Or maybe another thing is you do that you modify the loss. If this point is between a white guy and like this one is a background, I would say it's a light purple guy, then it should be either white or light purple. Either one of them, not black. So you should modify loss so that everything in here, you put a sample right here, and if it is white and it's okay, and if it's a light purple it's okay, but if it is black or red or orange, then you have some loss defined to that. You can do something like to make it perfect, but you can, I think if you stick with the original naive data set representation, it still works pretty well. In fact, after some tuning, you can get a better result. For example, I have contained a few examples inside the course repo. You can see a lot of files there, like let me see here. This A1 plotting, A-bit, and A2, I will say A2, they are the example file. And this one is for the 24 by 24 Chinese font. You just sell. We have different images right here. These are all A-bit images that I collected. You can use this as well, but you can collect the one that you actually like. So this is the result. If I do some support vector machine or neural network, we can get a result like this one. And this is a result. This one is actually a very common things like because this has numbers on it. So this is a typical way to do the super resolution things. Typical example for doing super resolution things. This result is not perfect, but it's still sort of smooth. And this one is I think is passable because the original one is really low resolution. But after you increase the resolution by using machine learning classifier, you can get something like this one. And this one is another approach that I did before. So this one looks a lot better than this one, because it has less like this zigzag things, and it also has an eyeball, sort of have an eyeball. The purpose of this course is to help you to visualize the machine learning, along with to paint something you like, but mostly to actually you can has a feeling of what the parameters of like support vector machine. You have the C, you have a gamma, since parameters that you can assign to your support vector machine. Those are the things help you to do so. And you should get 100 or nearly 100% accuracy on your original low resolution data. So even if you got 100% low resolution data, you will get something as poor as this guy. And this one is not good actually. So you need a lot of fine tuning. You can achieve good result for either support vector machine or the neural network. You can try different feature space like polynomial feature, IBF feature, or maybe some customized features as well to get a feeling how this feature works and how even your training. Your goal is to have 100% training accuracy on your low resolution data. That is your goal. That is one. The accuracy you need at least some kind of accuracy to finish your homework. So you have to at least adjust your model to have 100% accuracy on your training data. That is a low resolution images. Okay, so let me first show the notebook step by step to understand how it works. Let me check. Okay. Let me first pick the A1 things here. Is this one okay? Okay. Let me walk through this code. So you can either use Matplotlib or Pillow to render your image. I have both way in both different notebook. So in this, the first one is the example for supervised machine, majorly for supervised, but you can easily replace the model to other classifier because this is scikit-learn. So we are using the Matplotlib, so I include a lot of different Matplotlib here. Also import Pillow because I need Pillow to load image. Although Matplotlib has the functionality to load images, but personally I am more familiar with Pillow, so I always use Pillow to load images. You don't have to do that, but for me it is easier. And in the first case, it is not even using a Pillow to load image. I'm using this majorly for the demonstration of loading a Chinese font. Use it for the binary, for functionality of NumPy to demonstrate the function of NumPy. I forgot if I taught this one in the NumPy course or not, but NumPy have a lot of different functionality to load binary data. Okay, I remember. We use NumPy to load the MNIST binary data. So this one is used for load. We're using it to load the binary data. Another kind of binary data. That is a Chinese font, which is popular back in 1990s, probably toward early 2000s. But right now we use TrueType font. This one is a ad hoc bitmap font format. I have to read a lot of documentary to figure out the file format, but it turns out we can use NumPy to parse it using this way. So let me just run it. Okay, so I'm using another word like a simpler one here, and of course you can also use the say the images here. And I'm using a function to see how many different colors are inside this image. So you probably don't want it more than 20 colors, because if there are more than 20 colors, it is difficult to do the classification. So here is, but we don't know which color it is. So I'm using this to see how many color it has. It turns out it has two colors, white and black, because we are using this guy. But if you are using a different images, we will return how many colors are contains in this image. So for example, let me load another image right here. Probably I should show this image as well, but okay. So it will have more than one colors. So the palette will have different colors. Now I will index them one by one, given each of them an index. But currently I'm using this as an example. Okay, so after I have a palette, I control a reverse palette so that I can control my dataset. I control my dataset X and Y, but the fact is, did I control my palette? Okay, palette. I recontrol my palette. and my reverse plate. Then I control my X and the Y. So the X is more like this guy. It contains the coordinate, each of the coordinate. So how about Y? Y is just 0, 1, 0, 1. If I reshape it into 24 by 24, resize, reshape. Oh, I reshape, yes. Maybe I should decrease the font here and see. No, not yet. Not good enough. Print. Okay, so you can see, roughly you can see the Chinese character right here. Because 0 is, I'm using 0 as black and white as 1. You can see white as 1. So you can see that. However, there are better way to do that because we can actually use the fancy indexing to do that. We can do that like reverse plate. And but it doesn't seem to be easy, right? Tuple X. Okay, so we can probably do this one. List X. Okay, maybe not that easy because we have to have a list of tuples. I probably can do map tuples and the list, but I choose not to do this anymore. Okay, reverse. Okay. Okay, no, I cannot do that because the plate is a dictionary, right? Oh, it is a list. Oh, it's a reverse is a dictionary, so I cannot convert. But okay, there probably are different way to do that. But okay, this one is okay. I kind of confused. For the other way around, we have another way to do that. And then we do this. We construct X to be float because we have to make sure it is a float number. And here, what I'm doing here is that I'm making it more white. Okay, so and then I use the NUSVC to do and use polynomial. Okay, I probably should not run it in live because I probably haven't run it yet. What went wrong here? Okay. Okay. Let's see if it works. So I didn't intend to run it lively. It's just because the image doesn't seem to run correctly, at least not for this notebook. So this one is for the map plotting. So I'm using a segmented color map from list so that I translate the plate into a color map. So that I can easily plot the things in Matplotlib. I will demonstrate another way to do that using Pillow without using Matplotlib. Okay, then I use NUSVC to run the training. It may take some while, and after that it will show the result. This is a failed result. It is possible you are getting a failed, but if you train it correctly, you will get things to be a nice. At least it looks kind of resemble the original one. Okay, another the following code are for other classifier like a baking classifier, nearest neighbor classifier. Since I do a lot of different experimentations, they are all work pretty well, and you can use this code to do the plotting. So this code is for your reference to do the plotting for the decision boundary. And here are some examples that I have done before. This is one of the disk for the desk icon, and for the small icon from early arcade console games. And this is for some icon from early games, for like 8-bit art work. And this one is probably for the probably for the Windows icon. And this one is for game art. So this is something that you can expect it if you do some tuning to your models. You can do some parameters. Another thing I cannot explain clearly, but when you do the tuning to your model, you can actually see what happens to the machine learning. And you can actually see what is the cause of overfitting. So that is the purpose of this homework. A lot of things that I cannot explain it verbally, or even if I can, you won't get it. But if you really try this homework and to see it visually, you will understand certain situations that happens when you train it. When your training is failed, it will help you to overcome the things that you will encounter in the future when training more complicated models. And there are even more issues, but there are something happens in the higher dimensional, because we are only working on lower dimensional things. So there are more things happens because certain thing only happens in higher dimension, but still you can get some, at least something also happens in low dimension. You can use this example to actually get a feeling and knowing how to solve the issue. And this one is similar, but we only use Pillow to do the plotting. So similarly, we got the Chinese character and we convert the things into float 32 and convert everything into torch tensor. Both the Y tensor and X tensor into torch tensor. And we use this to construct a dataset. This is a customized dataset. The reason that I construct this dataset is because, you can actually use tensor dataset directly, but our data only has very limited number, and our model is small. So what I want is every batch is a whole batch, because I only got something like less than 1,000 samples. I only got less than 1,000 samples. So each batch contains the whole data set inside. But if I do so, it will run the progress bar certainly like flash every second. It will become the bottleneck. And even if you disable the progress bar, you can disable progress, but I still want to see the progress. Because I'm not using TensorBoard right here, I still want to see the progress. So instead, this may not be the best way to do so, but I can use dataset to simply construct the way I want. I simply subclassing the dataset, and you can see that I repeat the dataset itself 3,000 times. So I didn't even need to shuffle it. So shuffle is false. I repeat the dataset 3,000 times. So every time I repeat the pixels one by one, because every sample is a pixel, and the base size is the size of the dataset itself. So every time it will fit into the whole dataset and repeat 3,000 times. So what I do is when I get an index, I get a reminder of the size of the x. So I get the true index and then I return the self xi and the self yi. So that's it. And the length is of course the self.x.shape 0 times the repeats, because I repeat 3,000 times. So it is kind of ugly because I have to write this code. It's long for this easier things, and you may not understand. It is not very readable because this is just a simple idea. Repeat the dataset 3,000 times, and I believe there are tools for doing these things. But instead, I'm simply writing a custom dataset. It's easy. It is easy to write. A little bit difficult to read, but it is very easy to write. And it achieves what I want. Okay, then I get a data loader. The data loader didn't do much things. It just simply take a dataset and run. And this is my simple classifier. I'm actually doing something a little bit like a gated, the gated network things like this one. You can use other architecture, or maybe you can use some pre-trained models like ResNet or something as well. But those things are CNN. You can still use CNN, but it's kind of difficult because you are not supposed to. You should not use CNN because everything you read inside is a coordinate. Your feature is coordinate. So try not to use CNN because using CNN may not make much sense, and you are not getting the benefit of what I'm expecting you to learn from this homework. Okay, anyway, you can write any simple networks, and you can to train it. I'm simply using the cross entropy, and I'm monitoring the accuracy here. So here is the accuracy matrix here. Let me see how it trained. The support vector machine. Okay, the training is done, but does it? Okay, it doesn't train very well. So this one is a fail. This one is considered as fail. You should at least make it work. You can use decision tree if you are really in a hopeless case. You are desperate. You can use decision tree, but please at least make it to be like work nearly 100% accuracy, like at least 90% accuracy on the original plot. Okay, so anyway, let's back to a neural network. So after I define neural network, you can see that I'm using a kind of a wrong way to do that because I define a network inside the Lightning module. The best practice is to define the module in another module and pass the model into this Lightning module. But anyway, I'm doing a quick thing, and I have configured my progress bar and do the training. And because I'm loading this from the notebook, so we cannot see the progress bar. But if you are running this code, you will see a progress bar and reaching a pretty near 100% or 100% accuracy. So here is the result. You got a 100% accuracy. This is a predict result, not the original one. This is a predict result. It is because it is 100% accuracy. So on the lower resolution, it is exactly the same as the original image, because our training accuracy is 100%. But even if 100% accuracy, you are not guaranteed to get a perfect output. But in this case, I'm getting this one. It's very okay. You can imagine someone writing in Chinese ink writing in this way, but perhaps this is not what we expected. But you can get things like this one. So another is you can see the list here of how I actually construct a testing dataset. I'm actually just making the resolution. I get in the X minima and the X maxima and making it more resolution to has 1800 by 1800. So I got tons of more different samples in between to do the interpolation, sort of like doing the interpolation. And because it memorized, the neural network memorized the low resolution, so it has to fill out in the things between. So it is a super resolution, but it may not be the perfect things that we expected. Another case, another example here is for the multicolor things. This one is easier because we know that the 1 means white, 0 means black. But here we have different color. How do we map different color into a result? I mean, we only the prediction is just index, but how do we use the index to translate into using a plot to into a image, color image? The thing is that I'm using fancy indexing here. That is what I do. This is why also the data loader things and the training, and we got certain accuracy. And you can actually, if you find that the training is not converted, you can control another trainer and run the training again to customize different epochs to see the results. And finally, we got accuracy 100%. So this is on training data. It still got 100%. But you can see that I'm writing it in one line using the fancy indexing. So this is a prediction. Prediction, we use something like y predict is using argmax to get the index of the prediction. Then because this is index and the plot is just simply a list, so we can convert it into an array, and using fancy indexing to convert into color codes, and just by reshaping it, we will get the image. And the last help part is simply resize it to be large enough so that we can easily see that. So this is the training data. We got 100% accuracy. However, on the testing data, it is not performing that well. It does not perform that well. But still, you can see that it still resembles the color and the shape of the original image, because it is correct on 100% on the training data, and the training data is kind of sort of split everywhere on the image, so it will have the same shape. It's just the detail is not what we expected. So this is what the regularization or other techniques can be involved into. This is not inside the data that provided in the repo. This is just something I get from the internet. It looks like a bitmap image, but instead it is quite large, and every little block is not a pixel. It is a lot of different pixels, and in fact it has, although it looks like just have like 5 or 4 different colors, it is in fact have a lot of different colors, because it has different yellow, different white, different black, different red. So how do we handle this image? We use clustering first. So first of all, because the size is huge, I use a simple way to resize it. Instead of using resize, because resize will interpret the colors, it will make things more complicated. So I simply do the sampling here, here. This requires a little bit of experiment, but I pick every 5 pixels. So I technically resize it to a much smaller one. I only pick 1 pixel for every 5 column and every 5 rows. And then we use k-means to reduce the number of colors. I simply count the numbers like 1, 2, 3, 4. It seems to have 4 colors, so I use k-mean to have 4 clusters. And that's it. I get my dataset pictures. So I do pretty much the same thing to control my dataset and do the training, and got 100% accuracy on the training data. And we got something like this one on the testing data. So you can try to certain level, like what I demonstrated before, using certain techniques for machine learning to make the picture a little bit better. But you still need to understand what is the actual things you need. In the real life data, it is more complicated because you cannot actually it is in a higher dimension. You cannot visualize your data easily. But in here, you can visualize your data and you know what you need. Because I know I need an eye right here, and I need my curve to be more smooth. So I can change my feature to be like polynomial features, to change my network architecture, or using regularization to make it a simple model, like things like that. But there are some limit of what you can do. At some point, you need to modify your data set. Like what I said, because we already know something like there shouldn't be anything between this guy and this guy should not be connected to each other. Then we need to modify our data set to prevent. Otherwise, it may be even easier or simpler to connect them together because they are all black. They are both black. So it might be easier to connect together, and it makes sense. So if this is something you don't want, you have to do something to prevent this to happen. So this example helps you to improve your skills to adjust architecture to change the model. So I hope you enjoy. Maybe it's not a very good thing to say, but I hope you enjoy the homework, because don't feel too much pressure about this homework, because I already provide you examples. So just feel fun to explore the training process and tuning the model to achieve the results that you want. That is the main purpose of this homework. I know this is my purpose for you to have this homework, but I want you to have the same purpose, because I know your purpose of writing homework is to pass this course, to get the high grade. So I'm making it easier. You don't need to worry about the bar of passing this homework. Is easier. You just follow this to change you can find an easier picture. You don't need to have any pressure. So I'm hoping you can. I'm doing my best so that you can enjoy to explore this homework to learn the things I am hoping you to. The skill I hope you to develop from doing this homework. Okay, so that's all for today's lecture.